so let's kind of look at that again. Where is that? Here, I think. Yeah, there it is. So we went past this, but maybe we need to look at this again, just real briefly. Okay, pen. There you are. And will be red. So raw water is going to have stuff in it like magnesium chloride, which is permanent hardness, and it's going to have calcium chloride, and it's going to have calcium bicarbonate, and it's going to have magnesium bicarbonate. These are all of our hardness species. And then I guess we should also have calcium sulfate as another type of permanent hardness, and magnesium sulfate. So this is really hard water, and it's got everything in it. It's got chlorides, it's got sulfates, whatever. And that is all going in. In the H2Z unit, what we end up, what comes out of the H2Z is, well, we're going to swap the hydrogen for the magnesium and for the calcium and all that kind of stuff. So what we end up with is HCl in an aqueous solution, which we call hydrochloric acid. We end up with H2SO4, and we end up with carbonic acid, H2CO3. And then you go, crap, that acid is going in the boiler, that sucks. So what we do then is we see what's going to come out of the sodium zeolite unit. And what's coming out of that one is going to be sodium chloride, table salt, right? Not a big deal. And we're going to get sodium sulfate, which is not a big deal because that's going to form in our boiler for using sodium sulfite oxygen scavenger anyway. And we're going to get sodium bicarbonate, NaHCO3, which is baking soda. That is basic. That can neutralize the acid. So let's take this thing and, oh, what happened there? There it is. Sodium bicarbonate plus all the various acids that are coming from the hydrogen zeolite softener are going to undergo neutralization reactions, giving us sodium chloride, sodium sulfate. Here, we're just going to keep the nitric acid off there, okay? Sodium chloride and sodium sulfate. So ultimately, that's what we've got going through here. We're going to have sodium sulfate, Na2SO4. We're going to have sodium chloride. These are not balanced equations. And we're going to have carbonic acid, H2CO3. So those are all going to go into the degasifier. The carbonic acid decomposes because it's unstable at atmospheric pressure. So vents to atmosphere, CO2, and then really what we get is just water plus these dissolved solids, which aren't a problem for us. Okay, so there's our little recap reminder about what's going on with the split stream dealkalizer. So we were going over the demineralizer and we said, well, what we have is an H2Z unit here, and this one here is an R.OH unit. And we had talked about how we are going to exchange ions. So the cations are going to get H2, the anions are going to get OH, and what we end up with is leaving the cation exchanger, we're going to have dilute hydrochloric acid, we're going to have carbonic acid, because this is what we get out of a sodium zeolite exchanger, right? Or pardon me, hydrogen zeolite. This stuff here, hydrogen chloride, hydrogen sulfate, and carbonic acid, that's what leaves a hydrogen zeolite softener. So H2SO4. And that's going to go through these plastic pipes here. And then it's going to go up through this pipe into the top of the anion exchanger. And the anion exchanger is going to get rid of the anions, the chlorides, the carbonates, the sulfates. So what leaves this one here is basically going to be H.OH, which we know as H2O. Okay? Zero conductivity, no TDS, no alkalinity. Well, and ideally zero silica. So if this one here has a strong base type of resin, it'll remove silica. Now it doesn't remove like 100% of the silica, but maybe 99.9% of the silica. And over here there's a little testing station where we would test two things. Number one, conductivity. Number two, there was actually a sample going to an online silica analyzer that would do a real-time silica analysis. And I got to tell you, I used to ask people, what would that water taste like? What would that water taste like? People say, oh, you don't want to drink it. So why don't you want to drink it? Well, the reason you don't want to drink it is it's got no taste. Well, there's another reason why you don't want to drink it is because it's so pure that it actually will dissolve the nutrients in your body that you need, right? Your body has minerals and things, and it'll actually dissolve the stuff, pull it out of your body. So, you spend your life drinking demineralized water, or you spend your life drinking distilled water. It's not good for you. You need to drink water that's got impurities in it. So, we had mentioned about a strong acid, or a SAC unit. And a SAC unit is very, very good because it also turns sodium ions into their hydrogen component. And so the effluent we get is always going to be those ones, so you should know that. Now, sometimes we can use a WAC resin. The W stands for weak, and you guys who worked in oil, you worked with WAC units, right?
Yes. Yeah, we have.
Yeah, so the difference with the WACs is they don't remove the sodium. So in other words, we're still going to get dissolved solids in our effluent. They remove the hardness, but they don't remove all of the ions, which is really, really good. I mean, we want zero hardness, right? We don't want calcium. We don't want magnesium. And a WAC will do that, but it does not eliminate TDS. Okay? Because any kind of sodium compounds are going to pass right through it. Now, why would we use a WAC instead of a SAC? Well, first of all, we're going to use the SAC because if we want zero TDS, if we want pure water, then we have to use a SAC unit. And so we find this in generating stations and things like that. But if you're working in a SAGD plant, we don't really care too much about the purity of the water. You just want to make sure it's got no silica and it's got no hardness in it. So we can use a WAC and it'll let the sodiums through. Then the other thing that the WAC will do, which really makes it cool, is it is super efficient. And by super efficient, what I mean is that if you put a kilogram of regenerant material into it, it'll exchange a kilogram of ions. Okay? So because it's super efficient, we use less regenerant, and we get longer regenerant, and we get long service runs. And where you got really crappy water, like you have in a SAGD plant, it's really, really good. Now, because it does remove calcium and magnesium, sometimes what we do is we put a WAC in front of a SAC. And so first of all, it goes through the WAC, and the WAC is going to get rid of the calcium, and it's going to get rid of the magnesium. And then all the SAC has to do is get rid of any of the other ions. So the WAC takes the bulk of the load, and the SAC just kind of does this final polishing. And because the WAC is so efficient, it's a good piece of equipment to have in front of your SAC. So next time you're thinking about whacking your SAC, keep that in mind. Okay, now we know about the SAC resin, and so then that's going to be H2Z. And then we got strong base anion resins. Okay, so now the strong base. So we also have a weak base resin, and they basically do the same thing, except that the strong base removes silica. And that's very important for a generating station, because I don't want any silica getting on turbine blades. And it's also very important where we have SAGD, like OTSGs. In an OTSG, we don't want that really hard silica scale. Silica scale is really a bitch in boilers. Okay, so a strong base anion resin is very good for removing silica. So as for regenerating, when we do the SBA, or pardon me, the SAC resin, we're going to use sulfuric acid. And when we regenerate the strong base, we're going to use sodium hydroxide. And that's where we officially left off. We left off here, we're talking about regenerating the darn thing, and when do we regenerate it? So there's a couple of things that we can do. On the left-hand side of the scale, we've got either pH, you can see there's the pH, or we have conductivity in microsiemens. There's our conductivity. And we also have SiO2 in ppm. All right. So we're going to start right here with the equipment that is just rinsed down. It's just gone through regeneration, and its service run is about to begin. So at the beginning of the service run, the silica is very, very low, almost non-existent. Conductivity, and I think that these should be considered more like a relative type of scales, okay? So they're not really the actual numbers that you see here on the left. So we got a certain conductivity, we got a certain SiO2, and we got a certain pH. Now, what we have, first of all, is a cation unit, which is going to be H2Z. And then after that, we get an anion unit, which is R.OH. So, what we would like to have happen is for the cation unit to become exhausted before the anion unit. So what we're going to do is make the cation unit a little bit smaller in capacity. So let's say that the anion unit is good for, 1 million grains. that's an old term. It just comes to mind. Just units, okay? A million units of hardness, if you will. Or let's say a million gallons. Maybe that's a better way. A million liters, okay? That's the capacity. This anion unit can exchange anions to a million liters before it gets exhausted. The cation, maybe we'll make it a little bit smaller. We'll make it for only 800,000 liters. So now what's going to happen is this one here is going to exhaust first, and we know what happens when the cation unit gets exhausted. We see the free mineral acidity. If this happens to be acidity, the acidity drops at the point of exhaustion. Or you can also say, by the same token, that the pH will increase, because we know acids have very low pH. So if the pH is increasing, that's also an indicator that the free mineral acidity is dropping, which means that this sucker's getting exhausted. What happens at that exhaustion point, or where it's starting to show some free mineral acidity drop off, what we're actually seeing is some sodium ions are not being exchanged. You'd expect them all to be exchanged, but these particular sodium ones aren't being exchanged. Okay. The anion unit doesn't care if sodium is coming in, because it only exchanges anions. What that means is that we're going to see sodium in the effluent of the cation unit, or the anion unit, pardon me. See lots of sodium there, and so the sodium that leaks through from this unit, we can pick it up as an increase in conductivity. So here's what we're going to do. Instead of waiting for this conductivity right at the end, the exhaustion point is about 200,000 liters earlier than the anion unit. That means 200,000 liters before the anion unit is exhausted, we start to see sodium, and we actually start to see conductivity, and we see the conductivity goes up. And when the conductivity goes up, we go, oh, time to regenerate. Even though the unit is good for another 200,000 liters, we're gonna regenerate it as soon as we see the sodium leaking through. So that's alternative number one in terms of how we regenerate them. The next way that we can regenerate it is if we have got equipment that is going to monitor the silica all the time, then we can have a 1,000,000 liter unit and another 1,000,000 liter unit. And what we're really concerned about is silica breakthrough. And if silica breakthrough occurs, then we shut it off and we regenerate. So what I'm saying is there are two different ways. We can either remove it from service because of high conductivity, which means that the cation exchanger is exhausted, or we can regenerate based on silica breakthrough, which means that the anion unit is exhausted. Either way. Now, where I used to work at the generating station, we had a continuous silica monitoring, and we also regularly measured our conductivity. Plus, we had what was called end of meter run. So we had it set for a certain number of liters of throughput, after which it would alarm. When the alarm came in, we had to be more vigilant. So we'd be watching the silica more, we would be looking at the conductivity more, and we're trying to squeeze the last drops of water out of that particular unit. And maybe when that alarm goes off, I'm going to take my standby unit, I'm going to rinse it down and get ready to put that one in service at a moment's notice. So when we when we regenerate, we always do the cation unit first, because the cation unit is going to give us backwash water for the anion unit. So cation first, anion unit second. And then as for the sequence, it's the same as with a sodium zeolite softener. We always backwash it to expand the bed and release the dirt and expose the resin to regenerant. Then we do some sort of a brine injection phase, whether that happens to be H2SO4 or whether it's sodium hydroxide. It's got to be the right material for the right unit. Then we have a displacement, which is also called slow rinse, where we're basically pushing the spent regenerant material out. We're going to rinse it to compact the bed, and then we place it back into service. So really, it's exact same as for sodium zeolite softener. Now, here is our mixed bed. And I'm going to start here. Here you can see that there's a bed of material that is a mixture of anion and cation materials, okay? And they're all intimately mixed together. So when the water flows through, basically what we're going to do is take this effluent from the demineralizer. And recall that the demineralizer is H2Z plus R.OH. Okay, so we're going to take that effluent from the demin, which is already demineralized, and we're going to give it a final polish. We're going to remove last traces of silica. We're going to make sure nothing has leaked through. We're going to give it that final polish. So in service, the water comes and it's in contact with both types of resin. So when it's time to regenerate, we're going to backwash. Again, we reverse the flow through the vessel. And in doing so, what is going to happen is the heavy resin, because the resins have two different densities. The heavier resin, which I believe is the cation resin, the cation resin is heavier. Even though it's just a tiny little bead, it's more dense, and after the backwash, it's going to go to the bottom. So for a mixed bed, the backwash also serves to segregate the beads into their two varieties. Then what we're going to do is, it's kind of silly. Oh, what did I do? I just closed it. I didn't mean to do that. And I had all those nice colors too. So here's the wacky thing, is that interface between the two beads, lo and behold, there's actually a collector there, okay? It's called an interface collector. And so for regenerating the cation resin, I'm going to take some H2SO4, because it's cheap and plentiful, and I'm going to put the H2SO4 of a 2 to 8% solution through there. And that's one of the fun things about doing it, is blending it till you get the proper solution. You guys are going to be doing water tests like crazy to make sure you get a proper solution. And so the acid then goes through the beads, regenerates them, and then ends up going out through the interface collector to waste. And then you wonder, but what if that gets into the anion resin? Isn't it going to wreck the anion resin? And the answer is absolutely it will. So what we're also going to do, and they don't show it in the picture, but I'm going to show it, is something called block flow. And block flow is just water it's demin water, and the block flow is always going through here so that the acid can't get into the anion resin. So the block flow water also goes into the interface collector and also goes out to waste. Then we got to regenerate the anion beads. Okay, so the anion beads are here. Well, now what we're going to do is we're going to take the caustic, and we're going to put caustic this way through a feeder mechanism, and it's going to feed caustic into that interface collector, and from the interface collector, the caustic is going to go to waste. But then you're saying, what about the cation beads? Aren't they going to get wrecked by the caustic, and we just regenerated them? What about those beads? Well, to protect those beads, again, we're going to have a block flow. And now the block flow is going to come this way. So the block flow is going to go through the cation beads to the interface collector, and it's going to block the caustic from going into the anion beads. So then after we've done this, what we're going to do is a displacement. And displacement is a very slow rinse. So we got some water coming in there, we got water coming in there, and they're both pushing very slowly. They're pushing their respective acidic and caustic leftover regenerant. They're pushing it toward that interface collector and out to waste. That could take a little while. That was, I recall that was about 60 minutes. I remember because my boss used to say, Dave, where are you at in regen? I'd say, well, we're at caustic displacement. And he'd say, good, come on up. We need a fourth guy for playing hearts. And that's what we did. We played hearts in the control room. So it was always during caustic displacement, you go and you do the card game. Then after that, we drain the whole thing down. We drain out everything that's left in there. And son of a gun, we've screwed up. You know how we've screwed up? We've left the cation beads on the bottom, and then we left the anion beads on the top. And that's no good. Like, that's not a mixed bed, is it? That's a segregated bed. Well, we got to do something about that. So what we're going to do is we're going to take compressed air. Yeah, they show a little blower here. We take the plant compressed air or nitrogen, and we blast it through there. Now that the vessel's empty, recall, like there's no water in it, but we blast the air in it, and we mix up the beads again, so we end up with a mixed bed. Then after that, we refill it and we vent it. And there you go, we're back in service. Okay, so that then is your mixed bed. It's an interesting piece of equipment. It's difficult to regenerate. I'll find you a picture of it. Okay, so this is the mixed bed here. So we had a SAC, we have an SBA. So the SBA is going to get rid of the silica. The SAC is going to get all of the cations. And then the mixed bed is going to give it a polish. And there's actually a gauge glass here, you can see. So that will tell us if we've got a good segregation of the beads during the backwash. And what we would normally find is right about there. That's where we'd see the interface between the two different types of beads. So we talked about degasifiers. Now what we may do is if we've got a SAC unit and we've got an SBA unit, so we've got a cation and anion exchanger, leaving the SAC, we're going to get some carbonic acid. And in order to lighten the load on the SBA, in between the two, we're going to take that carbonic acid, we're going to put it through a gasifier or carbonator or aerator, whatever you want to call it, and that's going to get rid of the H2CO3. The CO2 is going to go at the vent, and so now only the free mineral acids have to be treated in the SBA. So sometimes we do have a decarbonator in between. It's not necessary. As you can see in the plant where I worked at, we didn't have a decarbonator. So one of the things is because we had the strong base also removes carbonic acid. So that's why we didn't have to worry about it. If we had a weak base, we would for sure have a decarbonator.